Okay, on this video we are going to solve a growing population model. So I'm going to dictate the problem statement. So a bacterial population is growing. It was observed that after 3 hours there was 400 bacteria, and then after 10 hours there was 2000 bacteria. Okay, what they are asking is what was the initial bacteria, because they are not given the initial bacteria. If they are given the initial bacteria, it will mean t equal to 0. Inciso B is asking what will be the number of bacteria in 15 hours. Inciso C is asking when the number of bacteria was 1000. Something that you can see here in inciso B and C is that here they're giving you the time and they are asking the number of bacteria. Inciso C is giving you the number of bacteria and they are asking the time with the question when. Okay, so something that really helps me when solving these kind of problems is that I usually write a timeline of events. So I'm going to do here the timeline of events. So the timeline of events is in t equal to 0. That was the initial. They are not giving us anything, but they are giving us something in 3 hours, and they are giving us something in 10 hours. Okay? So in 3 hours, they are saying that there was 400 bacteria. So somewhere here, 400. So this is the point in 3 hours. In 10 hours, they are saying there are 2000 bacteria. This point in this time. So it is something like this. Okay? Now, inciso A is asking what was the initial bacteria. So if we extrapolate this, it will be something like this. So this point is actually inciso A. The initial number of bacteria. Inciso B is what will be the number of bacteria in 15 hours. So somewhere here, 15 hours. Okay, so what they are asking is about this point. So that is inciso B. Alright? And then inciso C is when was the number of bacteria equal to 1000? Okay, because this is 2000 and this is 400, then it should be somewhere here. So they are giving you the 1000 bacteria, but they don't know what is the time. So that is inciso C. Okay, this give me an overview of what the problem is and what they are asking. Okay, so what I'm going to do is use the model. The model of the population growing is P of t equal to the constant exponential of kt. Okay? Check this out on this problem and this growing model. We have two constants. The constant of the integral when you solve the differential equation, and the constant k of the proportionality. And that is why we are given two initial conditions, in 3 hours, in 10 hours. Okay, so let's calculate the constant c and the k. So let's replace the value of the first point is p of 3 is equal to 400. But p of 3 is equal to the constant exponential of k times 3. Okay, so the other point is in 10 hours equal to 2000, so p of 10 hours is equal to 2000, and that is equal to the constant exponential of k times 10, where you replace the value of 10 in the time. Okay, so as you can see there, you have two equations and two variables, the constant k and the c. What I'm going to do is a division. What I'm going to do is this equation divided by this equation. So it's going to be the c exponential of 10k divided by the c exponential of 3k. That is one side. And the other side is going to be 2000 divided by 400. Okay, let's see what can cancel. We can cancel the constant, so that is why I made that division, because we get rid of one of the variables. And the only variable left is the k. Now, exponential divided by the same exponential, well, this is going to be exponential of 7k equal to, here, these two zeros cancel, 20 divided by 4 equal to 5. Okay, from there, we can calculate the value of the k. So we will apply the natural logarithm on both sides to cancel the exponential, and the 7 goes as a division. So the value of k is just the natural logarithm of 5 divided by 7. Okay, so the model, well, we just calculate the value of k. What about the value of the constant c? Okay, all we have to do is to replace this in this and calculate the constant. We can calculate it here or we can calculate it here. It doesn't matter because it's going to be the same constant. I'm going to do it in the first, so it's going to be the constant is equal to 400 divided by constant c, well no, sorry, exponential of the 3 then times the k, the natural logarithm of 5 divided by 7. And according to the calculator, that is going to be equal to the calculator, okay, 200.6. I'm going to get rid of the 0.6. It's going to be just 200. Why rounded? Because there is no 0.6 bacteria. The bacteria are integer numbers. There is no half bacteria or 0.01 bacteria. It's just one bacteria or no bacteria. Okay, 200. Okay, so my model is going to be something like this. P of t is equal to, once we know the value of the constant and the k, is going to be 200 exponential of kt. The value of k is the natural logarithm of 5 over 7 the time. Okay, so that's it. So we have the model. We have the personalized model because this is the general model for any growing population, growing model or decay model. But this one is the model that fits in this condition. So it is a personalized model. Okay, now let's answer the question. So inciso A is asking what will be the initial bacteria. So what they are giving us is the time equal to 0. They are asking about this time. So that is very easy, engineers. All you have to do is just P of 0. P of 0 is 200 exponential of 0. Okay, and the initial population happens to be the constant c. So that is the inciso A already answered. Now let's answer inciso B. So what will be the number of bacteria in 15 hours? So again, they are giving us the time. So all you have to do is just P of 15. That it should be bigger than 2000 at least. Okay, so that is going to be 200 exponential of the natural logarithm of 5 divided by 7 times 15. Okay, if we do that in the calculator, the calculator is going to be, just hold on. Okay, the answer is 6,292, and that's it, without the decimals, because we are going to consider the bacteria as integers. Okay, so 6,000, it makes sense because it's bigger than 2,000 and it is growing exponentially, so it's not linear, it's exponential. So 6,292 bacteria. Okay, inciso C. Well, inciso C is is more tricky because they are giving you the number of bacteria, and then you have to calculate the time. So what they are asking is, inciso C, is what will be the time so that the number of bacteria is 1000. So that should be between 3 hours and 10 hours. When? That's the question. Okay, so be careful here. The model is 200 exponential of the natural log of 5 divided by 7, the time. Okay, so what we have to do here is from this equation to clear the time. Okay, so I'm going to pass this to the other side. Two zeros goes away. 10 divided by 2, 5. Once again, 5 equal to the exponential, 5 exponential of the natural log of 5 divided by 7 t. Okay, to eliminate this exponential, we have to apply the natural log on both sides. So the natural log of 5 is equal to the natural log of 5 divided by 7, the time. Okay, I can see that the natural log is cancelled, so the time is equal to the 7 passed as a multiplication, 7 hours. So that's the answer. In 7 hours, there was 1000 bacteria. Now you can see here, from 3 hours to 7 hours, there are 4 hours, and the increase was only 600 bacteria. But from 7 to 10, 3 hours, and it was the double of that. So you can see it's not linear, it is an exponential. But here is just the answer of inciso C, here the answer of inciso B, and here the answer for inciso A. Okay, on the next video we are going to cover a problem with the radioactive material. See you.